Right, today we wanted to continue the discussion that we started in the last two sections, where we talked about partitioning and finding areas and looking at different ways of doing that. Well, the thing we're going to use and develop here is called the Riemann sum. Now remember, in this case, f of x equals the square root of x. That's this graph. And we break it up into partitions. Now in the last section, we made all the partitions the same size. That doesn't have to be. They can be any size. But the area here is going to be the sum of each of the rectangles. Okay, so the rectangles have width and height. Okay, so the y value is the height of the rectangle. And the delta x's are the width, but we call it delta xi because they're not all the same width. And the limit as n approaches infinity of that summation is the area that we found out last time. It is the area. So if we have, again, our function f of x squared, or square root of x, going from 0 to 1, and we're going to let ci, remember we had to find ci, so ci is the right endpoint, so that's 0, okay, and then it's going to be 0 and then I over n. So when we do that and square it, we get our ci. So delta x would be consecutive terms subtracted. That's how they get this. So the limit is delta, as n approaches infinity, of the summation of I going from 1 to n of f of ci, right? That's the square root of. So the square root of I squared over n squared. Delta x, that was 2i minus 1 over n squared. They've done that work for you. So because this is looking at the limit as n approaches infinity, right, we look at where n is, and we've got the square root of n squared in the bottom and n squared, so we've got 1 over n cubed, because the summation is going from I to n. We can get the things are not I out here. So now we have the square root of I squared, which is I, times 2i minus 1. That gives me 2i squared minus 1. I squared had a formula, n times n plus 1 times 2n plus 1 over 6, back in the first section of this chapter. I, n plus 1 over 2. Do the arithmetic on them, take the limit, and we get 2/3. And so the area under this curve is 2/3. Now that sum, not the limit part of it, but that sum piece, summation of I going from 1 to n of f of ci delta xi, is called the Riemann sum. So if you have a closed interval and you have a function and you've partitioned it, then the partitions don't have to be the same size, right? But the summation of I going from 1 to n of f of ci delta xi is called the Riemann sum of f with partitions delta. Now I wrote delta to show you that they're not all the same size. Right? And so that is what a Riemann sum is. Okay, we've worked with it, we've played with it, but how does that help us any? Well, the Riemann sum and a thing called the definite integral are related. So here's the definition of the definite integral. If you have a function on a closed interval, the limit of the Riemann sum, here's the Riemann sum, summation of I going from 1 to n, of the function working on ci delta xi, the limit of the partitions going to 0. That's the same as n going to infinity. But now we're talking about x, and that's why we want to put it here. That limit is the integral of f of x dx from a to b. It's called the definite integral. A is the lower limit of integration, b is the upper limit of integration. So this is called the definite integral. Okay? We'll talk in the next section of how to evaluate that. Just want you to see that there's such a thing. It's called the definite integral. Okay? The definite integral. Okay? So definite integral is related to area. Definite integral is related to area under the curve. Okay? Related to area under the curve. We should do this first. Here's evaluate this definite integral. Integral from -2 to 2 of 2x dx. Y equals 2x is that line from -2 to 2. So -2, 4, 1, 2 are the endpoints of that line segment. So that means the integral, the definite integral from -2 to 1 of 2x dx, right, is the limit of the Riemann sum. So if we do what we did before, we're going to keep the partitions nice and pretty. So we're going to take -2 and 1, subtract them, that gives you 3, 1, upper limit minus lower limit, all over n. There's your delta x. C, we're going to start at the far end point, which is at -2, and then it's plus delta x I, right? Back from the previous section. So this definite integral is the limit as delta are going to 0, the summation of I going from 1 to n of f of x delta x, so it's the limit as n approaches infinity, of the summation of I going from 1 to n of f of c. Well, c is -2 plus 3i to the n. The function is 2x, so 2 times that. So 2 times -2 plus 3i over n times delta x, 3 over n. So we've got -4 plus 6i over n times 3 over n. So we've got a 2 and a 3, that's 6 over n that we can factor out. So it's -2 plus or minus 2i. The summation of -2 is -2 times the summation from 1 to n of 1. We've already found out that that summation is n, so it's -2n. 3 over n, summation of I going from 1 to n of I, which again was I plus 1 over 2. And we end up with this limit, so it equals -3. So this definite integral from -1 to 2 of 2x dx is -3. Now, definite integrals can be used to find area. All definite integrals are not area. Obvious point. Area can't be negative. So this definite integral can't be the area being, the answer being -3, this is not the definite integral that's finding me area. But if you have these conditions, you have a continuous function, and it's non-negative, which means the y, no negative y values, it's above or on the x-axis, on a closed interval, then the area of the region from A to B is the definite integral from A to B of f of x dx. So it's definite integral, so that's area. So we can use the definite integral to find area, even if we can't define a definite integral right now. Here's an integral from 1 to 3 of 4 dx. So y equals 4. Y equals 4 is a horizontal line. And we're going from 1 to 3, so this is our region. The function is continuous. The function's on a closed interval. And all the y values, okay, are greater than, in this case they're all 4, so they're greater than 0. Therefore, this is the area under the curve. Well, this is just a rectangle, so the area is 2 times 4. So I know that this definite integral from 1 to 3 of 4 dx, its answer is 8. Okay? Definite integrals are always numbers. Definite integrals are always numbers. Integral from 0 to 3 of x plus 2 dx. Well, y equals x plus 2 is a line. It goes through 0, 2, and has a slope of 1. We're going from 0, x value of 0, to an x value of 3. Well, if the x value is 0, the y value is positive. The x value is 3, the y value is positive. So all the values on this function are continuous and positive. Therefore, this integral, this definite integral, is area. Well, we can figure out this area. It's a trapezoid. We can find the area of a trapezoid. It's 1/2 the parallel bases. Well, that's 2 and 3 added together, right? Or 2 and 5, sorry. 2 and 5, this height, added together, times the width, which was the 3. And so you get 21 halves, or 10 and 1/2 square, whatever. Okay. So sometimes to evaluate a definite integral, we can just use geometry. Here's the integral from -2 to 2. So from -2 to 2 of the square root of 4 minus x squared. Well, 4 minus x squared, the square root of it has to be a positive number. It's continuous, and it's the top half of a circle. And so it's continuous, positive, closed interval. Therefore, that integral is the area under the curve. Well, this is half of a circle. So a circle's area is pi r squared. R is 2. So pi times 2 squared, and half of that gives me 2 pi. And I've evaluated that definite integral. So definite integrals can be used to find areas. Definite integrals can be used to find areas, right? Two special integrals. Okay? If you're going to the integral from a to a of f of x dx, it's always 0. Because if you're going from a to a, your width of your region is 0. And the width is region, there's no area. And so that's, also the integral from b to a of f of x dx and the integral from a to b of f of x dx are the same number value, but they're the opposites of each other. Okay? So the integral of the sine of x dx. Sine of x dx is a continuous function. We're going from pi to pi. Okay? Well, since we're going from pi to pi, remember what the sine curve looked like. But now we're going from pi to pi, so we're not going anywhere, so there's no area under the curve. Therefore, by this definition, that's 0. And the integral from 3 to 0 of x plus 2 dx is the same as the integral from 0 to 3 of x plus 2 dx, but it's the opposite of it. In the previous problem, we did the integral from 0 to 3 of x plus 2 dx. We found out that was 21 halves. Therefore, by this theorem, this integral would have to be minus 21 halves. It would have to be minus 21 halves. If we have the integral from a to b of f of x dx, and we have some number c that's between a and b, then the integral from a to c of f of x dx, and the integral then from c to b of f of x dx, if you added them up, gives you the integral from a to b. Here's a region, continuous, all the y values are positive, so from a to b, so here is the area of the region. Well, is it the area from a to c and the area from c to b? When you put them together and add them up, give you the whole area? That's what it just says. Right? That's what it says. So the integral from -1 to 1 of absolute value of x dx. Well, from -1 to 0, absolute value is the opposite because it's negative, so it's going to be negative x dx, plus from 0 to 1 is x dx. Right? And if you know the shape, don't have it here, okay? If you know the shape, it's a triangle, okay? And we can find the area of the triangle, and we can evaluate this definite integral. Definite integrals are always numbers. I can identify that definite integral by using geometry. last couple of things about definite integrals. If you have a function, dx, the integral from a to b, and you multiply the function by k, that's the same as taking the integral and then multiplying by k. And if you have the sum or difference of two definite integrals, two functions in a definite integral, you could take the definite integral of the first guy, the definite integral of the second function, and add them or subtract them. And very much what we said about derivatives. Constants flow through derivatives. Constants flow through limits. Constants flow through integrals. Derivative of sums is the sum of the derivatives. Well, the integral of sum is the sum of the integral, is what we have there. Right? And so, last thing to finish off this section. If you have a function, integrable, non-negative on a closed interval, that means the integral from a to b of f of x dx is the area, which makes it greater than 0. So the integral from a to b of f. If f and g are integrable on that same guy, and f, term by term, the y values are less than or equal to the y values of g. So here's the y values of f, and they're smaller than all the y values of g corresponding. Therefore, the definite integral from a to b of f of x dx will be smaller than or equal to the integral from a to b of g of x dx. The area under the larger function will be bigger than the area under the smaller function, is what it's saying. So, Riemann sum, definite integrals, we now need to figure out how to evaluate them, and we'll do that in the next